Geoscience professor John Valley, left, and research scientist Kuki Kitajima collaborate in the Wisconsin Secondary Ion Mass Spectrometer Lab WISC-SIMS in Weeks Hall. Photo Jeff Miller. Researchers at UCLA and the University of Wisconsin-Madison have confirmed that microscopic fossils discovered in a nearly 3.5 billion-year-old piece of rock in Western Australia are the oldest fossils ever found and indeed the earliest direct evidence of life on Earth. An epoxy mount containing a sliver of a nearly 3.5 billion-year-old rock from the Apex Chert deposit in Western Australia is pictured at the Wisconsin Secondary Ion Mass Spectrometer Lab WISC-SIMS in Weeks Hall. Photo Jeff Miller. The study, published December 18, 2017 in the Proceedings of the National Academy of Sciences, was led by J. William Schoft, professor of paleobiology at UCLA, and John W. Valley, professor of geoscience at the University of Wisconsin-Madison. The research relied on new technology and scientific expertise developed by researchers in the UW-Madison WISC-SIMS laboratory. The study describes 11 microbial specimens from 5 separate taxa, linking their morphologies to chemical signatures that are characteristic of life. Some represent no extinct bacteria and microbes from a domain of life called archaea, while others are similar to microbial species still found today. The findings also suggest how each may have survived on an oxygen-free planet. An example of one of the microfossils discovered in a sample of rock recovered from the Apex Chert. A new study used sophisticated chemical analysis to confirm the microscopic structures found in the rock are biological. Courtesy of J. William Schoft. The microfossils, so called because they are not evident to the naked eye, were first described in the journal Science in 1993 by Schoft and his team, which identified them based largely on the fossil's unique, cylindrical and filamentous shapes. Schoft, director of UCLA's Center for the Study of Evolution and the Origin of Life, published further supporting evidence of their biological identities in 2002. He collected the rock in which the fossils were found in 1982 from the Apex Chert deposit of Western Australia, one of the few places on the planet where geological evidence of early Earth has been preserved, largely because it has not been subjected to geological processes that would have altered it, like burial and extreme heating due to platotectonic activity. But Schoft's earlier interpretations have been disputed. Critics argued they are just odd minerals that only look like biological specimens. However, Valley says, the new findings put these doubts to rest. The microfossils are indeed biological. I think it's settled, he says. Using a secondary ion mass spectrometer SIMS at UW-Madison called IMS-1280, one of just a handful of such instruments in the world, Valley and his team, including department geoscientists Kuki Kitajima and Michael Spikuza, were able to separate the carbon composing each fossil into its constituent isotopes and measure their ratios. Isotopes are different versions of the same chemical element that vary in their masses. Different organic substances, whether in rock, microbe or animal, contain characteristic ratios of their stable carbon isotopes. Using SIMS, Valley's team was able to tease apart the carbon-12 from the carbon-13 within each fossil and measure the ratio of the two compared to a known carbon isotope standard in a fossil-less section of the rock in which they were found. The differences in carbon isotope ratios correlate with their shapes. Valley says, if they're not biological, there is no reason for such a correlation. Their C13-Toc12 ratios are characteristic of biology and metabolic function. John Valley, professor of geoscience, is pictured in his office in Weeks Hall. Photo Jeff Miller. Based on this information, the researchers were also able to assign identities and likely physiological behaviors to the fossils locked inside the rock, Valley says. The results show that these are a primitive, but diverse group of organisms, says Schoft. The team identified a complex group of microbes, phototrophic bacteria that would have relied on the sun to produce energy, archaea that produced methane, and gamma proteobacteria that consumed methane, petrols believed to be an important constituent of Earth's early atmosphere before oxygen was present. UW-Madison geoscience researchers on a 2010 field trip to the Apex Chert, a rock formation in Western Australia that is among the oldest and best preserved rock deposits in the world. Courtesy of John Valley. It took Valley's team nearly 10 years to develop the processes to accurately analyze the microfossils. Fossils this old and rare have never been subjected to SIMS analysis before. The study builds on earlier achievements at WISC-SIMS to modify the SIMS instrument, to develop protocols for sample preparation and analysis, and to calibrate necessary standards to match as closely as possible the hydrocarbon content to the samples of interest. In preparation for SIMS analysis, the team needed to painstakingly grind the original sample down as slowly as possible to expose the delicate fossils themselves, all suspended at different levels within the rock and encased in a hard layer of quartz, without actually destroying them. Spicuzza describes making countless trips up and down the stairs in the department as geoscience technician Brian Hess ground and polished each microfossil in the sample, 1 micrometer at a time. Each microfossil is about 10 micrometers wide, 8 of them could fit along the width of a human hair. Valley and Schoff are part of the Wisconsin Astrobiology Research Consortium, funded by the NASA Astrobiology Institute, which exists to study and understand the origins, the future and the nature of life on Earth and throughout the universe. The apex fossils are scrappy, hard to find, difficult to study. They are abundant but charred, shredded, overly cooked. Tiny bits and pieces are common, but generally nondescript. Short 2 or 3 celled fragments are rare and easy to overlook. Many tooled specimens are few and far between, and fossils that could be called well preserved, like those of the Gunflint and Bitter Springs deposit, are non-existent. Were these remnants not so remarkably ancient, they would not merit much attention. J. William Schoff, Cradle of Life. Studies such as this one, Schoff says, indicate life could be common throughout the universe. But importantly, here on Earth, because several different types of microbes were shown to be already present by 3.5 billion years ago, it tells us that life had to have begun substantially earlier. Nobody knows how much earlier, and confirms it is not difficult for primitive life to form and to evolve into more advanced microorganisms, says Schoff. Earlier studies by Valley and his team, dating to 2001, have shown that liquid water oceans existed on Earth as early as 4.3 billion years ago, more than 800 million years before the fossils of the present study would have been alive, and just 250 million years after the Earth formed. We have no direct evidence that life existed 4.3 billion years ago, but there is no reason why it couldn't have, says Valley. This is something we all would like to find out. UW-Madison has a legacy of pushing back the accepted dates of early life on Earth. In 1953, the late Stanley Tyler, a geologist at the university who passed away in 1963 at the age of 57, was the first person to discover microfossils in Precambrian rocks. This pushed the origins of life back more than 1 billion years, from 540 million to 1.8 billion years ago. People are really interested in when life on Earth first emerged, Valley says. This study was 10 times more time-consuming and more difficult than I first imagined, but it came to fruition because of many dedicated people who have been excited about this since day one. I think a lot more microfossil analyses will be made on samples of Earth and possibly from other planetary bodies. The research was supported by the NASA Astrobiology Institute at the University of Wisconsin-Madison and the Center for the Study of Evolution and the Origin of Life at UCLA. WISC-SIMS is supported by the National Science Foundation EAR 1355590 and UW-Madison.